presentation. So the first speaker is Sam. So he's a PhD student in the Mechanobiology and Medical Devices Research Group at the University of Galway. He holds a bachelor and a master degree in biomedical engineering from the University College of Dublin. He specialized there in medical devices design, biomechanics, and computational modeling. And his PhD research aimed to develop multi-physics computational modeling and deep learning approaches for predicting the outcomes of transcatheter aortic valve implantation. So, Sam, the floor is yours. And this is your presentation.
Thank you so much. Thanks for the introduction. My name is Sam Boxwell. I'm a PhD student here at the University of Galway. I'm going to present a little bit about my PhD research today, which is on developing advanced multiphysics computational modeling approaches and deep learning to evaluate the effect of calcification-induced transcatheter heart valve underexpansion. So sorry for that very mouthful of a title. Okay, I'll just jump straight into the introduction. Okay, so the aortic heart valve is a trileaflet structure. It's located between the left ventricle and the aorta. Its main function is to open and close to maintain unidirectional flow throughout the left side of the heart. However, aortic stenosis is the most prevalent valvular heart disease in developed countries. It's characterized by narrowing of the aortic valve due to calcification on the leaflet, which prevents normal valvular function. It's defined as a degenerative disease of the aortic valve, but recent studies have shown that genetics, inflammation, and biomechanics all play a role in its development. So in recent years, transcatheter aortic valve implantation, or TAVI, has emerged as the most common form of treatment for aortic stenosis. So during this minimally invasive procedure, a transcatheter heart valve is delivered to the aortic valve. Typically, it's the catheter is inserted through the femoral artery and tracked up to the aortic valve, where it is deployed over the disease-native valve, which we can see here. So when a patient presents with aortic stenosis, the clinician first needs to develop a procedural plan. One of the first key decisions in this is choosing an appropriate device size. This is typically based on measurements of the aortic annulus, which is shown here in blue. The chosen device is then sized relative to the aortic annulus. However, in many cases, a degree of intentional oversizing is applied to ensure adequate anchoring between the device and the native anatomy. So the device is then implanted over the disease-native valve. However, calcification on the disease-native valve can actually prevent full expansion of the device, resulting in underexpansion of these devices. Over the last year, lots of clinical studies have emerged to show that underexpansion is linked to a number of post-implantation outcomes, including paravalvular leakage, which is the backflow of blood between the device and the anatomy, also stroke and structural degeneration of the bioprosthetic components. But we don't really know why this happens, which kind of begs the question, are these increased rates of post-implantation complications caused by altered valve mechanics and blood flow? Recently, balloon post-dilatation has been proposed as a possible solution for preventing underexpansion of these devices. This involves the inflation of a balloon within a deployed device. However, this is an unplanned procedure. It's only conducted if suboptimal expansion or paravalvular leakage are identified. And furthermore, the clinical efficacy of this procedure is relatively unknown. So how does this procedure actually impact the expansion of the valve? And are there implications for the long-term durability of the device when this procedure is performed as well? Over recent years, computational modeling has emerged as effective tools for predicting the outcomes of TAVI. These studies typically utilize finite element analysis to predict deformation on the device or stress and strain, computational fluid dynamics to look at flow across the device, or fluid structure interaction approaches which couple deformation and flow. The use of these models aligns with various global initiatives proposed by the FDA and the EU to, I suppose, progress towards in silico clinical trials of medical devices. So considering all this together, the global objective of my PhD is to evaluate the effect of calcification-induced underexpansion of transcatheter heart valves. To address this objective, we develop multiphysics models of TAVI to assess the impact of underexpansion on valve mechanics and blood flow. We then develop patient-specific models to assess the impact of balloon post-dilatation on frame expansion. And finally, we apply deep learning approaches to determine calcification features that are predictive of post-implantation outcomes, in particular paravalvular leakage. So we begin specific aim 1 by creating a finite element model of a TAVI device. This is a commercially available device, and it consists of a self-expanding nitinol stent and porcine pericardium leaflets. These are the material models that we use to model those. I won't really get into those details. So using the model, we simulate TAVI by firstly crimping the device to 10 millimeters. This replicates the stage of the procedure where we're attaching the device to the minimally invasive catheter. We then simulate device deployment using a two-step process by firstly removing an upper catheter to deploy the top portion of the device, and then unsheathing of a lower catheter to deploy the bottom portion of the device into an idealized aortic annulus. This deployment configuration replicates the unique deployment mechanism of the specific device that we're modeling. Next, we simulate the cardiac cycle through multi-physics modeling, utilizing both finite element analysis and computational fluid dynamics approaches. Firstly, we apply physiological pressure waveforms to the surfaces of the bioprosthetic leaflets to simulate opening and closing of the valve. And we model contact between contacting surfaces during this procedure. We then extract device dynamics from these simulations for integration in independent computational fluid dynamics simulations, which we use to look at flow across the device. So one of the most important steps of developing these models is validating them. So we conducted validation with different experimental testing, including radial force, high-speed imaging, and particle image velocimetry, where a model showed really nice alignment. If you want more details on this study, the preprint is up there in the link. So once we validate our models, we wanted to look at how transcatheter heart valve oversizing impacts leaflet mechanics and hemodynamics. So to do this, we deployed the device in two idealized models of aortic stenosis, which we classify as nominal sizing, where the perimeter of the device is the same size as the perimeter of the annulus, and we have an oversizing model where the perimeter of the device is larger than the aortic annulus. So firstly, as expected, we found that transcatheter heart valve oversizing reduces expansion of the device, potentially resulting in underexpansion. And you can see that here when we compare the teal curve and the dark blue curve there over on the left of the graph. So next we looked at leaflet mechanics, and as you can see, oversizing had a notable impact. The leaflets exhibited clear pinwheeling, which is actually this twisting motion in the center of the leaflets, and that you can see here. And this pinwheeling effect actually caused increased maximum principal strain in this region, which is linked to reduced device durability and may promote bioprosthetic tissue degeneration in vivo. We also found that oversizing had a notable impact on hemodynamics around the valve, resulting in early mainstream flow separation, recirculation, and vortical flow in the functional valve region. This resulted in increased oscillatory shear index on the surfaces of the bioprosthetic leaflets. These hemodynamic conditions promote thrombus formation, calcification of the bioprosthetic components, which may actually explain the reduced device durability associated with underexpanded devices noted in recent clinical studies. Downstream of the device, we found that oversizing increased the instantaneous viscous shear stress. This is linked to platelet damage, which again may contribute to increased stroke risk noted in recent clinical trials. So we looked at lots of different other factors, which I won't mention here, in terms of stent deflection and hemodynamics as well. We also looked at how elliptical device deformation impacts valve mechanics, and you can see more details in this paper that was just published. Okay, so now that we've shown that oversizing causes underexpansion, we wanted to see if balloon post-dilatation could actually prevent underexpansion of these devices. So to address this objective, we began by creating patient-specific models of aortic stenosis from a retrospective cohort of patients. We then simulated TAVI by, again, following our workflow by crimping the device and then deploying the device into the diseased aortic stenosis models, which we can see here. Following simulation of device deployment, we then simulated balloon post-dilatation. So as I mentioned, this is the procedure where a balloon is inflated within a deployed device, hopefully to improve expansion and reduce leakage between the device and the anatomy. This was modeled by applying a pressure of 3 atmospheres to the inner surface of the balloon. We then removed the balloon to allow the elastic recoil of the aortic root. And we repeated this study across a distinct patient cohort where the patient models are shown here. So as I mentioned, validating these models is a really important step. And we did this with retrospective outcomes for this patient. So we looked at post-TAVI CT for 3 patients, and we calculated the expansion index, which is a function of the nominal device size to the deployed device size. And we looked at the ellipticity index, which is a ratio of the minimum to the maximum diameters of the ellipse. And we looked at this across distinct planes of the stent, which we can see here. And this is the results for patient 1. And as you can see, our model showed excellent alignment with the post-TAVI CT, predicting both expansion and ellipticity indexes within 10% of post-TAVI CT. And those findings were similar across our entire patient cohort as well. So we also conducted in vitro testing to validate our model. Briefly, this involved developing a 3D printed patient-specific model of aortic stenosis, deploying the device in this model, and then looking at the hemodynamics across the device using a pulse duplicator. This is basically a system that replicates cardiac flow in vitro. And as you can see, our model showed really nice qualitative alignment between the in vitro hemodynamics as well. So once we've validated this, we use our modeling framework to assess how balloon pulse dilatation impacts frame expansion. And as you can see, it resulted in a more expanded and circular device when compared to no balloon pulse dilatation. This result was consistent across our patient cohort, showing increased expansion and reduced ellipticity, with significant differences, particularly at the inflow at plane 1 and at the annular levels at plane 2. This suggests that balloon pulse dilatation may actually improve hemodynamics post-TAVI and reduce the risk of thrombogenic events as well. As I mentioned, one of the main concerns associated with balloon pulse dilatation is its potential impact on device durability, as when the balloon expands, there's potential to cause tissue damage and tearing of the bioprosthetic components. However, when we examined the stresses in the leaflets during post-dilatation, we found that using an undersized 22mm balloon notably reduced the leaflet stresses when compared to using a nominal sized balloon, which is the same size balloon as the device. Importantly, this shows that balloon undersizing actually retains the benefits of post-dilatation by improving the expansion of the device without impacting long-term durability as well. We also looked at the impact of balloon pulse dilatation on the occurrence of paravalvular leakage post-TAVI by calculating the gap area between the device and the native anatomy, which is shown here in red. And our models predicted that balloon pulse dilatation notably reduced the paravalvular gap area at both the midplane and the annular level, which we can see here. Okay, so now that we've shown balloon pulse dilatation, it's associated with reduced paravalvular leakage, we wanted to develop or look at developing a more proactive approach for patient stratification. And see if we could actually identify features, anatomical features that were linked to paravalvular leakage in a retrospective cohort. So to address this objective, I utilized a previously developed deep learning framework in Harvard Medical School to develop digital twins of aortic stenosis, which you can see here, which uses deep learning for CT-based segmentation. From this, then I extracted aortic root, native valve and calcification features, and also used open source pyradiomics to calculate or to extract radiomic features linked to calcification. We wanted to see if any of these features could predict paravalvular leakage in a retrospective cohort. So first we conducted a feature importance analysis. This determined that the most predictive features of paravalvular leakage were related to device oversizing and annular ellipticity. Notably, 21 of the top 30 predictors related to paravalvular leakage were calcification features, where features relating to the spatial coverage of calcification and density heterogeneity of calcification emerged as top predictors. And this further highlights the importance of device calcification interactions in post-implantation outcomes in TAVI, and there's more work ongoing with this to develop predictive models to use those features to predict PVL in a retrospective cohort. So to conclude, in the study, we utilized multi-physics modeling to show that oversizing altered device mechanics and hemodynamics by increasing pinwheeling, flow separation, and shear stresses linked to thrombogenicity and degeneration in vivo, We also showed that under expansion can be prevented through effective balloon post-dilatation, where balloon sizing may actually obtain the benefits of post-dilatation without actually impacting device durability. And finally, we showed that calcification is a key predictor of paravalvular leakage in a retrospective cohort of patients. Collectively, these studies show that device calcification interactions shape post-TAVI outcomes, whilst underscoring the role of multiphysics modeling and deep learning for patient stratification, which may be applied for optimized procedural planning and ultimately improved clinical outcomes. So with that, I'd like to thank my supervisor, Professor Alicia McNamara, our research group, all our collaborators, and Research Ireland for funding. Thank you all for listening.
It was very interesting, a very nice video.
Yeah.
Does anyone have questions? Yes.
Thank you.
I'm interested in the calcification. So is that like a symptom of the disease?
Yeah.
And is it known what causes that?
Yeah, so calcification would be like the main cause of aortic stenosis. So it's typically thought to be like the aortic valve, it opens, I think, 30 million times a year. So it does degenerate over time. So it's common in elderly patients to present with aortic stenosis. And that is typically the development of that calcification. And you can get that within the valve. So it's a degenerative thing, really. So the tissue will eventually degenerate over time. And then you can get kind of calcium particles passing through the tissue and calcifying over time. It's thought that biomechanics plays a role as well. There's certain pathologies of the aortic valve, like bicuspid aortic valve, for example, and that's a disease where the aortic valve presents with 2 functional cusps instead of 3 functional cusps, and that alters the biomechanics and hemodynamics of the valve, and that condition is actually associated with accelerated calcification. So those patients typically present with aortic stenosis at a much younger age. So it's a combination of factors between degeneration of the native tissue over the many years that it has to function, genetics, and also biomechanics as well. Thank you.
Patrick?
Thanks, it was a really interesting talk. My question actually relates to calcification as well. Is there any way to model calcification post implant or like post procedure?
Yeah, it's really, that's like an area of active research at the moment. So I would say that we have more of a clear understanding of what happens to the native valve and how that calcifies. But I think I showed an image in the introduction as well. That calcification process actually happens again to these devices over time because they don't have active cells to, I suppose, help combat the calcification. They degenerate at a much quicker rate than our native valve. And we don't really know the mechanisms that cause the degeneration of these bioprosthetic components. But there's some research going in terms of looking at like different signaling pathways and implementing those in computational models and looking at, I suppose, classification in kind of a mechanobiological role. So how do these mechanical cues that the bioprosthetic tissues receive, how do they cause degeneration? But it's an area of active research where there's not really too much known as to why it happens to the actual devices. If that answers your question.
Yeah.
Okay, cool.
Thank you, Sam, for the presentation. I think the first thing is a comment. I would definitely need your help to create such an amazing figures. I really like them.
Thank you.
I really like them.
Thank you.
My question is maybe beyond the scope of your research, but you are really looking at the structural approach of this valve, this stent.
Yeah.
Have you looked also at the material side of it? Like what could be the material that could allow for this shape changing and opening the valve? Is there something today which works well, or is there like progressing?
Yeah, in terms of the material of the stent, or okay. Yeah, so there's like different devices that are currently commercially available. So the device that we're modeling is a self-expanding nitinol device, and that device basically relies on the radial force of the nitinol to basically push out that calcification of the diseased native valve and achieve optimal expansion. But like we kind of showed, sometimes those materials need kind of the extra force with the balloon to help push that out. But there are other devices available. They're actually balloon expanding, so they're made of cobalt chromium, and they typically have I mean, because they rely on the balloon, they push it, the balloon pushes it out, and then the stent plastically deforms. They typically are subject to less under expansion in clinically, but there's other complications linked to kind of the kind of more brute force approach of pushing open the valves. So you can have things like aortic root injury, or you can have permanent pacemaker implantation, which is a additional complication to TAVR, where actually the metallic stent, it pushes out so much on the aortic root that can actually disrupt the conducting system of the heart. And then a patient needs to get a pacemaker afterwards to restore the natural rhythm of the heart. Those are the two main materials that are used currently. And I'm pretty sure I was at a conference last year, and I think people are starting to look at magnesium based approaches as well, but they're much further down the line from being clinically implemented. Okay.
In the cohort that you used, did you separate or did you notice the difference of the valve? You know, because the patient it could be native just valve or replaced valve, which could be from pit or calf. You know, did you separate the difference between this structure? Because I think it could be a 50.
Is between the deep learning stuff, or is this the modeling cohort? Yeah, so that was actually, we looked at bicuspid aortic valve patients. We included 3 patients who presented with bicuspid aortic valve disease, and they all had varying amounts of calcification present as well. So it was someone who was presenting with, I suppose, aortic stenosis to be clinically treated for the first time. So they hadn't received any device or any procedure prior to the TAVI procedure to help resolve that stenosis. In terms of the cohort, or in terms of the, yeah, well, it will directly affect, like, the native valve needs to be replaced because it's not functioning properly. I mean, the ideal valve replacement would be something that would directly work like a healthy aortic valve over a long period of time, but that's a challenge for engineers currently. Yeah.
Very fabulous work.
Thank you.
Sorry, I don't understand. I don't know too much about the AI work, but I'm just very curious about, like, how do you include the clinical samples into your deep learning research, and what's the criteria for it? As well, the data sets for the deep learning work is quite important. Like, different data sets will generate different results.
Yeah.
And the second thing is, do you think it's need to find more clinical evidence and to follow some clinical outcomes and to verify what you predict by your research work?
Yeah, that's a really good question. So in terms of the deep learning and the clinical data, so all the clinical data that we utilized was from Brigham and Women's Hospital in Boston. So I was over in Harvard, and we utilized the deep learning framework they'd previously developed and validated on 700 patients who presented with aortic stenosis. So all of those patients were tricuspid aortic valve. They presented with varying degrees of calcification. It was the first valve replacement surgery that they received. And we kind of matched for male and female populations as well. So that was kind of the most, and actually they all received the same device as well. So that we could basically, like, because the outcomes are very device specific as well. So all the 700 patients that we modeled, or that we looked at with the deep learning with, were all received the same device as well. And then in terms of the validation, yeah, that's a really good question. So I think that we would need to validate, even like we've done 3 patients with our multi-physics models. If this was something to be implemented clinically, you would need a lot more than that. There's actually clinical trials ongoing with different companies who are looking at using pre-procedural planning tools to optimize TAVR or this procedure. But those platforms have been in development for many years. And they're just kind of being more clinically implemented now, but there's a a trial currently ongoing with 40 patients, where these patients are the procedural strategies that the clinicians are choosing are based on the outcomes of those models, and those models have been validated over a number of years with different outputs. There's lots of different stages to validating these models. Like, you need to validate them with in vitro, you need to validate them with retrospective outcomes, and it's a very long process. And then you have to do uncertainty quantification and stuff as well. Yeah. Thank you.
I think with time we'll move on to the next speaker, but thank you so much.